Myself, Dr. S. David AMALRAJ, Assistant Professor, PG and Research Department of Chemistry, St.Joseph College of Arts and Sciences, Autonomous, Cuddalore. Today, you are going to see how to calculate the wavelength by using Woodward rules. So these are the two scientists who said to calculate the wavelength theoretically. One is Robert Byrne Woodward, another one is Louis Frederick Fisher. So these two scientists have set the rule to calculate the wavelength theoretically. In 1945, Robert Byrne Woodward gave certain rules for correlating wavelength of maximum absorptions with molecular structures. Later, in 1959, Louis Frederick Fisher modified these rules with more experimental data, and the modified rule is known as Woodward-Fisher rule. So these rules work well for dienes and polyenes with up to 4 double bond or less. So we can apply this rule with less than 4 double bond of diene and polyenes, or 4 double bond of diene and polyenes. These rules is to calculate the wavelength of maximum absorptions of a compound in UV spectrum, based empirically, have been called the Woodward-Fisher rule or Woodward rule. This may be differ from observed value by 4 to 5 nanometers. So for theoretic value as well as instrument value, so may be differ from 4 to 5 nanometer. It's a very important point. Longer the conjugated systems, greater the wavelength of absorption maximum. So if the conjugated system increases, the wavelength of absorption also increases. That is maximum. So according to the rule, the lambda max of the molecules can be calculated by using the formula lambda max is equal to base value plus substituent contributions plus other contributions. So this rule, this pi rule, you have to know to solve the problems. First one is homonomer diene, second one is heteronomer diene, third one is exocyclic conjugated double bond, fourth one alkyl substituent and ring residue, fifth one extended conjugated double bond. First, homonomer diene. In homonomer diene, conjugated double bond are present in the same ring and having cis-oil configurations. We call this as a homonomer diene. See here in the molecular first structure. See the double bond or alternate double bond. So we call that as a conjugated double bond, single bond, double bonds. So we call this molecule as a homonomer dienes. The conjugate ring present in the same ring. So we call this as homonomer diene. So second example. So two rings are fused together. So the conjugate ring, double bond, single bond, double bond. So double bond, conjugate double bonds are present in the same ring. We call this as homonomer dienes. When come to heteronomer diene, the conjugate double bond not present in the same ring. See the example, first example. See double bond, single bond, double, it has conjugations, but the conjugate double bonds not present in the same ring. So it extends to the second ring. So we call that diene as an heteronomer diene. So second example also be double bond, single bond. Next, the conjugate extended to the second ring, double bond. So it has conjugation, but the conjugate system not present in the same ring. Call that diene as an heteronomer diene. And come to third one, exocyclic conjugated double bonds. So you have to know the basic things. cyclic ring. See here the cyclic ring projecting outside CC bond we call as exocyclic double bond. See here I am giving an example on drawing. See the sector. So if a cyclic ring projected outside the CC double bond, we call this an exocyclic double bond. So like this, projecting outside means we can tell that it is an exocyclic double bond, exocyclic conjugated double bond. So like this, the carbon-carbon double bond projecting outside a ring are called exocyclic double bond. See here, it has first one examples. First one. See here the first one. First you have to see whether it has conjugation or not. So double bond, single bond, double bond, it has conjugation. It has on cyclic ring, a cyclic ring projecting outside on CC double bond is there. We call this projecting outside CC double bond we call as exocyclic conjugated double bond. So second examples. And come to second examples, two rings are fused together. So it has conjugate ring. When we focus on A, so when you focus on A, projecting out C, the projecting outside, it has one CC double bond. Whereas when focus on B, the B ring outside projection, there is no exercise, there is no projection outside the door. The next to the position is that it has double bond. So it has only one exocyclic double bond. And come to the third one examples. So here this has a conjugate system. When focusing A, so when focusing A ring, outside the A ring it has one double bond. See here it has one double bond. So exocyclic double bonds. When you focus B, B ring fused with A. When B ring fused with A, when you focus B, B outside C it has one exocyclic double bond. So for this molecule it has two exocyclic double bonds. Likewise, there's so many examples are given. See for these examples, a double bond, two ring are fused with a double bond. So when you focus A projecting outside it has one double bond. See here this, when you focus on A, the ring outside it has CC double bond. Whereas when focus on B ring, see it has outside C it has CC double bond. So for this molecule it has two exocyclic conjugate double bond. Okay, so likewise you have to see the exocyclic conjugated double bond. And come to the fourth one, alkyl substitution and ring residues. Alkyl substitution and ring residue. Only the alkyl substitution and ring residue attached to the carbon atom constituting the conjugate system of the compound are taken into account. See here, both ring are present means the longer wavelength we have to take as a parent values. So the longer one is 253 nanometer, that is the home-mounted diene systems. So the ring residues. So these are the influence of neighboring saturated carbon on a double bond or at a site of an unsaturations. We call that as a ring residues. Fifth one is extended conjugated double bond. So parent values. See here, cis form, double bond, single bond, double bond. We call this as a parent value because we are talking about only the Woodward shift to calculate diene system. Diene means only a double bond, single bond, double bond system. Apart from the parent values, if conjugate system getting extended means we call that bond as an extended conjugated double bond. We call that as an extended conjugated double bond. So see here the first point, two double bonds separated by a single bond are conjugated if a third double bond is separated from one of the original pair of the double bond by a single bond. See here, if this one is a third double bond is separated from where? One of its original pair of the double bond by a single bond. The three double bond represent as an extended, the third one we call as extended conjugated system. So 5 you have to know before to calculate the Woodward-FIESER. So this one is the pi. So first one is homonodiene, second one is heteronodiene, third one is exocyclic conjugated double bond, fourth one is alkyl system or ring residue, fifth one is extended conjugated double bonds. So these five systems you have to know, then only we can calculate theoretically by using this rule. So these are the table you have to memorize for what are the substitutions we have to apply. So if for alkyl substitution we have to use 5 nanometer, for exocyclic 5 nanometer, for double bond extending we have to use 30 nanometer, for alkoxy, chloro, bromo 6 nanometer, for acyloxy 0, likewise thio and also amino group 60. So we have to memorize this table. So when you memorize means we can easily solve the problem. So first problem we are going to, I'm giving example lesson 2 3 dimethyl 1,3 butadiene. So first draw the structure and have to see whether this molecule have conjugate system or not. So 1 2 3 4. So it has alternate double bond. So this molecule is an conjugated system. And see it is whether a closed chain system or open chain. So it is an open chain system. So it is not a homonodiene. It is not a homonodiene. It is an heteronodiene. So the base value is 214 nanometer. Okay. Second, we have to check whether it has exocyclic. It is doesn't have exo because this molecule is not a cyclic. It is an open chain system. So this molecule doesn't have exocyclic double bond. Third one, whether it has a ring residue or alkyl substitution. So you have to see when the substitution present at the conjugate system, we call as an alkyl substitution. When the substitution present at the conjugate system, we call that as an alkyl substitution. See here, first one, second double bond, it has one methyl group, like the third double bond has another group. So it has two alkyl substitutions. So 2 into 5 for one alkyl substitution 5 nanometer. So it has two alkyl substitution 2 into 5 10 nanometers. Whether it has extended conjugated dienes, no, it doesn't have extended conjugated diene. So totally it has the base value is open chain system 214 nanometer, and it is an there is no ring residue. It has only two alkyl substitution. There is no exocyclic. There is no external conjugate. Totally, it has 214 nanometer plus 10, 224 nanometers. So calculated for this molecule is 224 nanometers. While this molecule, when you run in UV, you get observed value around 226 nanometers. Second examples, another examples. See here, a double bond, single bond, double bond. So this molecule has a conjugate system. Okay, so here when come to the, it look like a transite forms. See here, it is an open chain system 214 nanometer. First double bond, it has two methyl substitution, and the third carbon it has one methyl substitution. Totally it has three alkyl substitution, 3 into 5 15, 229 nanometer. Another examples. So this see the conjugate system not present in the same ring. We call this as an heteronodiene. So the heteronodiene, the parent value is 214 nanometer. Okay. So the whether see it has exocyclic, see it has one exocyclic. So where A ring, this one is A, this one is B. Okay. When focusing A, outside the ring, you see here it has one exocyclic. When focusing on B, outside ring there is no exocyclic. See the conjugate system next to the, so outside the double bond you have to focus. So there is no B outside, there is no exocyclic. Totally this molecule has one exocyclic. Okay. Whether it has alkyl substitutions, there is no alkyl. So this it's not an alkyl substitution. Only the conjugate system. If conjugate system substitution, any substitution means we call that as a substitution, alkyl substitution. So this methyl group is not present in the conjugate system. So it is present separately. So this don't calculate this methyl group value. Okay. So when come to the ring residue, so for see here double bond, single bond, double bond. Okay. So see first double bond. See the adjacent carbons. So the adjacent carbon is free. So it has one ring residue RR, and focusing on the second one. So this one is a second ring residue 2RR, and this adjacent carbon springs. So 3R. So totally for this molecule has 3 ring residues. For one ring residue 5 nanometer, 3 ring residue is 3 into 5, 15 nanometers. So there is no extended conjugate dates. Okay. So totally 234 nanometer for this molecules. Likewise, you have to work out for these problems. So this is an open chain. This is an heterodine 214 nanometer. It has 3 ring residues 1, 2, and as well as 3. And it has one exocyclic. So this one is A ring, this one is B. Okay. So it has one exocyclic. This one is an exocyclic. For conjugate system, it has one ether system. So for this 6 nanometers, totally 240 nanometer. Likewise, you have to work out these problems. Come to these examples. For this molecule, say a double bond. This is an open chain system, double bond, single bond, double bond. It is an conjugate system. It is an open chain system. So it has first 215 or 214 nanometer. It has 2 ring residues. So adjacent double bond. See, and come to the double bond. This carbon is free and this carbon is free. It has 2 ring residue. Okay. So 2 into 5, 10 nanometer. And see here one alkyl substitution, 2 alkyl substitution. There is a double bond. So in conjugate system, see this one is on alkyl substitution, this one is an alkyl. It has 2 alkyl substitution, 2 into 5, 10 nanometers. This one is a ring outside projecting. There is one exocyclic, so one exocyclic 5 nanometers. So totally 240 nanometers. Likewise, work out these problems. Okay, for this problem, base values, see here this molecules 2 is there, that is homo as well as heteronadiene. We know that homonadiene is a longer valence, so we have to take the parent values of homonadiene to 50 nanometer. Okay, ring residues. See here first double bond, the second one, third one, this one is fourth one. Okay, first double bond adjacent carbons, this one is free, first one ring residue. Second double bond is this carbon is free, 2 ring residue. Third one this carbon is free, 3 ring residue. And fourth one this one is free. And for this ring residue, this carbon is free. So totally 5 ring residue. And it has this one is the parent value. Okay. So remaining extended double bond, it has 2 extended conjugate double bond. So 2 into 30, 60 nanometers. That's 3 exocyclic. So when you focusing, so A, B, C. A projecting outside as one exocyclic, B projecting outside C it has one exocyclic, C projecting H has one exocyclic. So totally 3 exocyclic. So totally 353 nanometers. Thank you.